Actually doing up to here. So we are looking at perturbation, in principle, that can depend on time. Then we looked at the states. We said that psi at t this was given by, okay, there is this time ordered exponential of I over h bar vi of t prime dt prime. Well, we started from 0 to infinity, 0 to t. Psi at t equal to 0. These are all interaction pictures. Now we say that this matrix element from some initial state to some final state n was equal to, up to a phase, these are interaction picture states. Well, it doesn't make any difference here. Then, okay, we started from this and said that let's look at the transition amplitude Cn of t was given by minus I over h bar from 0 to t dt prime and vi of t I. This was the first correction. And then in particular, we said that if we look at, let's say, Cn of t squared, then we looked at the, okay, this gave us approximate energy conservation for large t times some coefficient times the energy conservation times t. This was linear in t plus some energy conserving Dirac delta. And if you remember this energy conserving Dirac delta, well, these results are valid in the case of a constant perturbation. The perturbation itself doesn't depend on time explicitly. This was the transition rate. Now, if you go to second order, and okay, so here we had this time-dependent part coming from sine squared alpha t divided by alpha t squared, if I'm not wrong. This was Dirac delta alpha t. This was the basic idea. Now, the claim in the book is that in the second order perturbation theory, we had minus I over h bar squared t1 we had inserted a complete set 0 to t1 and vi of t1 m which was equal to up to certain constants 0 to t dt1 e to power I on. There were some 1 over en minus ei terms, v I n mn I omega n I of t minus e to the power I omega m n of t. Now, the first term is just like what we have at Cn1, because this is the same exponential dependence in the first term. So we just took this one, and as you pointed out, we just ignored this term. Sorry, it's not mn, mi. And the claim was that, at least the explanation in the book, I'm not so much convinced myself, to be honest, is that in this sum, EM is not even approximately equal to EN or EI. Since this is not satisfied, the Dirac deltas that will lead from that exponential will not be satisfied, so we won't get any significant contribution. To be honest, I don't buy that. Because when you look at that summation there, you have all the terms. But at least that was the claim in the book. Let's correct this properly. You see, one of the problems we are having, at least up to this point, is what do you mean by large T? So the claim here is for large enough T. And furthermore, since we are looking at time, our expressions are time dependent, we cannot even send T to infinity. It's just large but finite, because eventually we also need to take the derivatives, etc. It's large but finite. So let's do it more properly now. More properly in the sense that we have this state I, at T goes to minus infinity. You see, up to here we are just setting at T equal to 0, we have our initial state, and let's see what happens after we turn on the interaction. Okay, so T equals to 0 is arbitrary. So rather than taking the final time T to be very large, because the important thing is how much has passed since the beginning. That's what counts. Let's send the beginning of our treatment, of our study of our state, to a very large time in the past. And of course, we still need to make sense of what this means, but that will clarify the issues. So this is what we have at T equal to 0. Furthermore, I will define a time-dependent potential, not the interaction picture, but the time-dependent potential. You see, this is our potential, the actual potential that we have, actual perturbation in our system. That is time-independent. I will add this term. And I will consider the limit as eta goes to 0. So we will see in a moment that we still need to take care about in which order we take the limits. So let me use this Ti. In the limit as Ti goes to minus infinity, and then we take the limit eta goes to 0. This is 0. So you see, if you remember our initial discussion of this external potential, what we said that we turn on the potential at T equal to 0, and then see how it goes. Here, I'm looking at a kind of a similar system. I'm looking at my system at the time T. In the long past, there was no interaction, but this time it's not a suddenly I change the perturbation, but gradually I change it. So that at T equal to 0, at least, it's exactly my potential. At a larger time T, it's not exactly my potential, but still it doesn't change much significantly from my potential. So let's see what this gives us. Let me just look at the second order correction directly. C2 of T will be minus I over h bar squared dt1 from minus infinity to T dt2 from minus infinity to T1. Now, the way this will answer your question is, you see, this integral over there is mainly from this limit of that T2 integral. Now I'm sending that to minus infinity. So basically that term will just disappear. So the claim of the book does have a piece of truth in it, let's say. But I don't really buy the argument. So let's continue. Let's see what this will bring. N Vi of T1, Vi of T2, I. We just inserted a complete set of eigenstates. And then we have e to the power I omega n m of T1, I omega m I of T2, e to the power I, no I, e to the power eta T1, eta T2. This is my potential. Well, let me evaluate the T2 integral. From minus infinity to t dt1, e to the power I omega n m plus, no, minus I eta T1 times e to the power I omega mi minus I eta T2 divided by I omega mi minus I eta. T2 goes from minus infinity to T1. Now in the lower limit, when T2 goes to minus infinity, due to that eta term, it goes to 0. So this is equal to minus 1 over h bar squared, sum over m, v n m, v m I, divided by I, well, let me also move the I here, omega mi minus I eta okay, let me just okay, there's one thing I need to take care of. You see, I have to single out the case when m is equal to I. I will separate it out. This is m is not equal to I plus minus I over h bar squared. Well, there's no sum, just the I contribution. Vni, Vmi, Vii, no, I will not separate that. No need. Because you see, as long as eta is finite, everything is finite. So the limit already takes care of that. I over h bar squared, sum over m, Vnm, Vmi, divided by omega mi minus I eta, minus infinity to t dt1, e to the power I omega nm minus I eta, T1 times e to the power I omega mi minus I eta, T1. which will be I over h bar squared sum over m v n m v m I divided by omega m I minus I eta minus infinity to t dt1 e to power I omega n I minus I eta t1. Well, if you want to be more formally correct, the eta in that exponent has a factor 2. There are two etas, but just changing the definition will not make any difference because eventually we will set eta to 0. And also, in fact, here, you see, we have 1 over x minus I eta, which can be written as x divided by x squared plus eta squared plus I times eta divided by x squared plus eta squared. Now, limit as eta goes to 0 of 1 over x minus I eta. Remember, this is, or let me write it in this form, x over x squared plus eta squared is what is called the principal value of 1 over x. That's the definition. And in fact, if you remember on Tuesday, I also used the fact that at some point, the principal value of 1 over 0 is 0, not infinity. Well, it's obvious kind of over here, because if you set x is equal to 0 on the left-hand side, first, and then take the limit, the left-hand side is 0 when x is equal to 0. Only when x is not equal to 0, the left-hand side just becomes 1 over, the ordinary 1 over x. That is kind of the definition of the 1 over x, the principal value. And this eta over x squared plus eta squared, you see, it is such a function that if you integrate over x, this is pi, independent of eta. Now, limit as eta goes to 0, eta over x squared plus eta squared. You see, if you look at the right, this function, if x is not 0, this function is 0. If x is 0, that function diverges. Yeah, that's kind of the property of the Dirac delta. But we also know that the integral of that function is just pi, independent of eta. Even in the limit as eta goes to 0, the integral should remain as pi. In fact, that is what tells us that this is pi times Dirac delta of x. But this is, if you like, the real part of 1 over x minus I eta. This is just the imaginary part of 1 over x minus I eta. So this identity we will be using quite often. So if you remember on Tuesday, we were also looking at the energy shifts, and I claim that this sum the imaginary part is non-zero, although everything there is real. Still, the sum has a non-zero imaginary part, basically because of this relation over here. You see, on the left, if you just straight away put eta is equal to 0, it's just 1 over x. It's real for real x. So it seems that there is no imaginary part, but because of, well, the minus I eta terms and the limits that we define, there is an imaginary contribution. Well, here on Tuesday's derivation or on our previous derivation, there is nothing imaginary there. And there's also this additional term that we throw away. But now this treatment makes why we can throw away the additional term and why do we have the imaginary part of this expression. And keep in mind that this the integral now is independent of the state m. So this is just a prefactor. But then all our claims in the previous derivations, that it's just like this one is just similar to C1 of t. It has similar in the sense that it has the same time dependence. And hence this is nothing but just and remember in C1 we had V I n times something. Now the only thing we need to do is to this V I n add this term. And well, the only thing you need to change is just the change VIN to VNI to VNI plus that sum over m. And then we had interpreted that as, well, this state I can make a direct transition to the nth state. Of course, we also have the conservation of energy factors in the rate at least. And then there is the other correction is the state I can make a transition to the state m, not necessarily conserving energy, and now from state m, it can go to state n. Again, not necessarily conserving energy in any of these transitions, but overall, there's an energy conservation. And this factor 1 over omega mi minus I eta is sometimes called the propagator. So we have the initial state, it makes a transition to the mth state, it propagates in the mth state, finally making another transition to the nth state. So if you interpret it like that, this is just a second order Feynman diagram. You see we had the ith state, nth state, here we have VNI, or we have the ith state, mth state, nth state, here we have Vmi, Vnm, and here we have the propagator 1 over omega mi minus I eta. And then the next term in this series will be 3 potentials. This is the C3. And again, this is I, M, K, N. Here we have VMI, VKM, V and K. And here we would get the 1 over omega mi minus I eta, 1 over omega km minus I eta. So basically, once you realize this, you don't even need to go through all those integrations, etc. So you can just write away whichever order term you want. Now again, I repeat, this is the case when the perturbation is not time dependent. Does that answer your questions? As I said, I don't really buy the argument in the book. This is a more concrete, more foolproof proof.
I've taken this course, lecture on this particular topic. This is my 3rd time now in 10 years. And every time the instructors had the same problem, which is exactly this exponential. They said, I don't buy the argument in the book. So yeah, there's something shaky there. Yeah. Very hand-wavy.
Okay, so let's continue with time-dependent potential. I mean, you see, eventually we will be aiming at atomic emissions and absorptions. So in that case, what do we do? I'm sure you have all studied in quantum mechanics. You have all these discrete energy levels. If you send some photon with a given frequency, it absorbs it, and it can emit that frequency, etc. How does that work? First, let's look at this general case. We have a potential which depends on time, has this particular dependence. We will look at the first order term. Quite often, especially if you are dealing with electromagnetic interactions, they are weak. So the first order term is usually dominant. So we need to find C1 of t would be just plus I over h bar dt prime, let's say from 0 to t. T will be large. Which will be I over h bar from 0 to t dt prime e to power I omega n I of t v I omega t plus which is so we have these two terms. Well, our earlier treatment already tells us that this will we will get a contribution from this exponent. If this term was alone, we will get a contribution from that one for omega ni plus omega almost 0, or En is equal to Ei minus h bar omega. Now, if this term was on its own, we would get a contribution to a transition rate if from states for which omega ni minus omega is 0, or En is equal to Ei plus h bar omega. Now we have two terms. If you just take the absolute value squared, etc., we will get the absolute value squared of the first term, which will give a contribution at large t only if this condition is satisfied. This is what's called the emission. Then we have the square of the second term, which we will get a contribution if this condition is satisfied. So the initial state absorbs an energy h bar omega and makes a transition to the nth state. If you want to get a contribution from the mixed term, the product of these terms, well, in that case, both of those conditions should be satisfied. Otherwise, you don't get a linear time dependence. You will just get some transitional rate processes. But those terms will be important only if both of these conditions are satisfied. But then you cannot have both of those conditions satisfied at the same time. So you will get only a dominant contribution from the first one in the case of emission, or the second one in the case of absorption. We can write right away the transition rates from the initial state to the final state with energies close to the n. It's just 2 pi over h bar in the case of emission, we should have the Vni squared. In the case of absorption, we should have V and V dagger Ni squared. The upper are for emissions, the lower are for absorptions, and then we have the Dirac delta or the density of states, whichever one you prefer. Okay, for emission, the upper sign should be plus. And again, the Dirac delta is not actually a Dirac delta, it's just the density of states, which will look like a Dirac delta in a real life situation. Now, there's one more observation we can make. You see, this V and I dagger is nothing but N V dagger I, or I V N dagger complete conjugate, which is V I N conjugate. But that means if we want to find, let's say, the transition rate from N to I, well, let's see, if you ignore the density of states, the emission divided by density of states for N this is actually equal to, this emission is V and I, so here it is the absorption divided by the density of states for I. So apart from the density of states, the emission and the absorption, they have the same rate. Their difference is due to the density of states, if they are different. So this is called the detailed balance. More or less the probability of emission and absorption are the same, and it's in fact just a direct consequence of this fact. Now, practically we have everything that we need to deal with the simulated emission and absorption of an atom, of an electron in an electromagnetic field. So let's just look at an electron. The Hamiltonian of the electron in an electromagnetic field. So what do you remember about the Hamiltonian of an electron in an electromagnetic field? How can we write the Hamiltonian of such a system? Not just the electrostatic potential, but there might also be a magnetic field in the system.
So, replace the canonical momentum P minus QA of.
So that's this one. So we can just open it up. This, if you like the electrostatic potential, you can take just like the Coulomb potential if you want, time-independent Coulomb potential, and then you just have an electron in an atom. This is our unperturbed state. Plus we have minus Q over 2 MC A dot P plus P dot A plus Q squared over 2 MC squared A squared. Now, later on we will come to that. This is, in general, very small. Just ignore. We will ignore that one. Now, in general, the vector potential A and the momentum, they don't need to commute. But the commutation is proportional to gradient of A, their commutator. If A depends on your position, it won't commute with the momentum operator if this is non-zero. But we will just we will choose a gauge for which that is zero. We will look at such vector potentials. So in that case, the Hamiltonian of the system is P squared over 2m plus Q of phi. Well, this is the unperturbed atom. And then we have minus Q over MC A dot P. This is H0. This is V. It depends on time t. Now that V of t, or let's say A, we can take just the plane wave or the cosine wave. Let me use the notation in the book. Is 2A0 epsilon hat, that is the polarization vector. And then we have the cosine k dot x minus omega t, which I can also write as A0 epsilon hat e to the power I k dot x minus omega t plus e to the power minus I k dot x minus omega t. But I'm practically done. You see, this is A dot P is now A0 epsilon dot P e to the power I k dot x or minus I k dot x e to the power I omega t plus A0 epsilon dot P e to the power I k dot x times e to the power minus I omega t. Now this is the problem that I had already studied. This is what I called V. This is what I called V dagger.
When we study classical electrodynamics, we have, if we take the polarizability series, right, as frequency dependent, we get to the Kramer's-Krennig relations, right?
Can you repeat again?
The Kramer's-Krennig relations that arise in classical, that's if your permeability or whichever epsilon depends on frequency, right, for the material. That's how you get it. Well, this is the material. In a sense, this is the EM field is interacting with. This Hamiltonian is the material that we're interacting with.
Well, we are not looking at this as in a material.
But what would change? Like, do we rescue, can we get Kramer's-Krennig relations from this sort of consideration, looking at the opposite thing, looking at the quantum version?
Here, if you like, we are just looking at a single atom, so there is no medium effects. Now, of course, when you want to go if you want to go to the effects of medium,
Mm.
there are a couple of things you can do. One is just look at the statistical physics of it.
Okay.
No, we are not doing any statistical physics here. That's one problem. The other option is from here you can look at the scattering of the photons from the atoms, a single one.
Mm.
In a medium, well, as the photon is propagating, it will be constantly scattering.
Right.
So you can just try to calculate the average effect of that scattering itself.
That's what this is also, though, right? I mean, this
No,
is
here there's just
we're
a single
looking at
one
right,
atom.
and we're looking at the transition in the atom.
Yeah.
Right. But at the same time, something happens to the field. The field is different now, and that should agree with classical.
You see, here we are not dealing with the field.
Right. But
We are not looking at what it does to the field. But what I think from here, what you can do is look at the absorption rate on the average, how much it will be absorbed. It will depend on frequency. And that absorption rate will probably give you some refractive index, etc.
I wonder if we can define like a microscopic refractive index, right? Like that makes any sense. Like refractive index for a single atom.
Well,
like what is that? What is that?
In principle, refractive index is a macroscopic quantity.
I know. Like, what's the limiting case of like a one atom scatter refractive index? What is that physically? Nothing.
You see, if you want to talk about refractive index, you have to be able to talk about the speed of light.
Mm.
There's nothing like that over. The light comes with the speed of light
Mm.
in vacuum, and once it's scattered, it still moves with the speed of light in vacuum. Now, at least the imaginary part of the refractive index is what describes the absorption of electromagnetic radiation in medium. So here you can calculate the absorption. Of course, you have to average it over all the atoms, etc. Okay, so let me just add the coefficients also. Here I have a minus Q over MC. Now, what is the transition rate? Well, this will be two pi over h bar, absolute value of transition rate to the nth state. Well, you can just look at either the absorption or the emission. The first one is the emission. So let's look at that one. Now we can do slightly more with this, but okay, so for example, in your problem, you see here, this rate depends on A0, which will determine the intensity of the radiation field we use. Especially if you want to study how this electromagnetic field changes in a medium, A0 will be changing. So you have to deal it separately. But at the same time, we have to come up with some property of this interaction of the electromagnetic field with the atom that is independent of the amplitude of the... so there will be certain effects which will depend on the amplitude of the system. Well, in this case, we see that if you double the amplitude A0, the transition rate becomes 4 times. But that doesn't tell us anything really about the properties of the underlying interaction. We can just change this rate by just changing the amplitude. There are also other properties of the underlying physical properties of the interaction which should be independent of A0. So that requires us to define something else other than this transition rate. So one thing you would like to, for example, know about this thing is the rate of emission of energy, or let me say, let me look at the absorption, and that it kind of makes more sense. Rate of absorption of energy per flux of energy. Well, if you just want to calculate the rate for a given energy flux, just multiply with the energy flux. And so this ratio doesn't depend on how much energy you pump into the system. This kind of describes, or it depends only on the properties of how electromagnetic fields interact with the atoms or whatever we have. Shall we give a break or continue? How do you feel? Okay, let's give a break, and then we'll continue calculating this one.